to discussion of local magnetism. So today is lecture number 16. Lecture number 16. So it's a semi-classical theory of local magnetism. Well, at the very first lecture I already mentioned that magnetism is purely quantum phenomena because it is either related to the spin, which is a quantum number, or it is related to quantization associated with the orbital motion, which is also a quantum effect. But today we are going to start with a limit of large spin. So what does semi-classic mean? So if spin is much larger than 1, and we will see on Friday that if we have a macroscopic magnetization in the system, it can behave as a classical vector. But suppose you have atoms with a non-filled shell, it's either D atoms or F atoms. So in principle, according to Kuhn rule, you start to fill the orbital such a way that you create large moment. And therefore, if the moment is sufficiently large, we can apply a semi-classical approach. I will told you that the operator S squared has eigenvalue S plus 1. We can always construct a theory choosing quantization axis such a way that your Z operator has a diagonal representation, matrix form representation, and in addition the operator S squared is conserved and its eigenvalue, the matrix of X squared is proportional to unit matrix, and the eigenvalue is S plus 1, which is S squared plus S, and if S is much larger than 1, this is approximately S squared, because we can neglect the term of the order of S compared to term S squared. Let me remind you commutational relations for S operator, namely S plus S minus is equal to 2 times S Z. Where S plus minus are always, if I don't write S, please, this is S x plus minus I S y. We have 3 components. If we divide the left-hand side and right-hand side of the equation by S squared, we will get that S plus divided by S squared, so S minus divided by S, commutator is equal to 2 times SZ divided by S times 1 over S. So if I will scale my operators to the value of spin, I see that in the limit S much larger than 1, I have a right-hand side 0 because I have additional 1 of the S multiplier. Therefore, in the large S limit, I can assume that the operator S plus normalized by S and S minus normalized by S are just 2 commuting operators. Well, let's therefore think about semi-classical spin as a sort of vector M, which lives on a sphere. So vector M has the components mx, m1, and mz, and m squared is equal to mx squared plus m1 squared plus mz squared is equal to m squared, is conserved. Therefore, I can assume that my classical vector m lives on a sphere. So this is my vector m or m capital. So this is z, this is x, this is y. So we are going to start with very simple Hamiltonian, which describes the effects of magnetic field on which describes the coupling between magnetic field and classical vector m. So the most simple Hamiltonian which we can imagine, this is just minus m dot h. Today, for the sake of unifying notations, I'm going to denote magnetic field by the letter h. And as usual, without losing generality, I will take my coordinate system such a way that the axis z is perpendicular to direction of magnetic field. Therefore, in this choice of basis, magnetic field has the only component which is along the z-axis. So the scalar product is minus mz times h. For the sake of today's lecture, I will consider to begin with magnetic field being constant, uniform, and time independent. So, what we are going to do, we are going to take this Hamiltonian, take Higgs distribution, and calculate average values of mz. So mz average, by the definition, the length of the vector is conserved, is integral over solid angle mz e to the power minus h over t is the temperature, divided by the integral over the omega e to the power minus h over temperature. This is Gibbs distribution, where omega is a solid angle. So d omega is sinus theta d theta d phi. I remind you that this is angle theta, this is angle phi, and we are working in spherical coordinate system. Mx is m sinus theta cosine phi, my, let me call it m. My is m sinus theta sinus phi, and mz is m cosine theta. So basically, what is written here is integral from 0 to pi sinus theta d theta, then mz is equal to m cosine theta e to the power minus and minus gives me plus m h cosine theta over temperature, integral 0 to pi d phi, divided by the integral from 0 to pi sinus theta d theta e to the power m h cosine theta over temperature, integral from 0 to pi d phi. Okay, this is what I'm going to compute, and of course I use the units that Boltzmann constant is equal to 1. Good. Is that clear what I'm going to do? To help me with the calculations, I will denote the denominator, which is, by the way, partition function, which is integral from 0 to pi sinus theta d theta e to the power mh cosine theta over temperature, integral 0 to 2 pi d phi. Okay, let me compute z, namely denominator first. Okay, first of all, nothing depends on phi. Therefore, I have a 2 pi after integration over phi. Then, as usual, I will denote cosine theta as x, and therefore the remaining integral is integral from -1 to 1 dx e to the power mhx divided by temperature. You remember, if I introduce a new variable, this is a minus d cosine minus dx, but the integral from 1 to -1, and therefore I flip the sign and I change the limits of integration. So this is a very simple integral. I will first make it dimensionless. So therefore I will multiply and divide by temperature over mh. So I have integral from minus mh temperature dx e to the power x. This is the simplest possible integral. It gives me 2 pi temperature over mh, and here I have e to the power mh over temperature minus e to the power minus mh over temperature. If I divide by 2 and multiply by 2, I recognize that here I have a cosine hyperbolicus, therefore I have a 4 pi temperature over mh sinus hyperbolicus mh over temperature. Good. Then let me see that the numerator, if I make a notation y, which is mh over temperature, here I have exponent to the power y cosine theta. Therefore, the numerator is equal to, if I take z and I take a derivative of z with respect to y, I will get the cosine theta. So m is m dz over dy, where y is equal to mh over temperature. Indeed, if I take a derivative, I get cosine, and I need to multiply by m. Okay, let me check this.
As an example, I don't get enough line.
Sorry?
I said I didn't get the last line.
First of all, I did not complete. I need to write for pi. What I'm saying is that my numerator is integral from -1 to 1 dx m times x e to the power yx times 2 pi. This is my numerator. Right? I can write it down as a 2 pi m d dy integral from minus 1 to 1 dx e to the power yx. Is it correct? Yes. Because I'm differentiating with respect to y, I get x, and 2 pi m is in front. Very simple. I would like to simplify my calculations. And partition function in this notation is 4 pi sinus hyperbolicus y divided by y. So therefore, my numerator is equal to 4 pi m d z over dy at y is equal to mh over temperature. And mz, do you understand what I'm doing?
Yes, getting better.
Just to be sure that you are familiar with my objects and you are familiar with what I'm going to get. So, mz is 1 over z, and numerator is 4 pi m dz over dy, at y is equal to mh over temperature. Z is equal to this, 4 pi cancels out, so this is y divided by sinus h y times m times d over dz sinus y divided by y. In principle, I can write it as m d over dy log sinus y divided by at y is equal to mh over temperature. mh over temperature. So, this is very simple equation. Let me just compute the derivative. Okay. Let me compute this line. So, mz average is equal to m y divided by sinus y, and I'm taking the derivative. So, cos y divided by y minus sinus y divided by y squared, and y is equal to mh over temperature. So altogether it is equal to m times the first term gives me cotangent hyperbolicus y, and the second term gives me minus 1 over y. At y is equal to mh over temperature. So this function, cotangent y minus 1 over y, has a name. It is called Langevin function. L mh over temperature. So I introduce the new function, very simple one, is cotangent hyperbolicus y minus 1 over y. So therefore, I got equation which says that mz average is equal to m times Langevin function mh over temperature. Good. Let's see how this Langevin function looks like. And therefore, let's study its properties. First property. Properties of the Langevin function. Lang J than function. So L minus y is equal to minus Ly. So this is odd function. So therefore, it's sufficient to study properties of this function for positive y, and then we take the mirroring from the point of view of central symmetric transformation. Second, let's discuss how this function looks like for the small argument. So L at y goes to 0. To do that, we need to Taylor expand. The Taylor expansion for cotangent is 1 over y plus y over 3. You can take in the book, you can take the cotangent is the fraction of cosine hyperbolicus to sine hyperbolicus, take expansion of them, or do whatever you like. I will write the next term by memory. So this is minus y 1 over y. So you see the divergent term cancels out, and we have y over 3 minus y cubed over 45. Indeed, we see that the function is odd function of y. And so, let's see how this function behaves at y goes to infinity. So we have a cotangent, which is e to the power y plus e to the power minus y divided by e to the power y minus e to the power minus y. This is a cotangent minus 1 over y. So I will write it at 1 plus e to the power minus 2y. 1 minus e to the power minus 2y. I multiply numerator and denominator by exponent to the power minus 1. Minus 1 over y. And then I Taylor expand, assuming that exponent is small in the limit y goes to infinity. So this is approximately 1 minus 1 over y plus 2 times exponent minus 2y plus and so on and so forth. So you see that the function is less than 1, so it is bounded from below and it is bounded from above. So the function, this is y, this is Ly, it is linear for small arguments, it goes like that, and it doesn't have any extrema, you can check it, and then it is central symmetric. So this is the behavior of Langevin function. Okay. Let's introduce the susceptibility, which is a response to the magnetic field.
Hello.
Yes?
Can you hear me?
Yes.
Yeah, so I have a question about the third behavior. I don't get why you keep the term 1 over y and exponent to the minus 2y.
Well, the exponent is originating from this. Just to say that exponent in the limit y goes to infinity is always much smaller than 1 over y. So, and this function is bounded from above. So basically, I can drop this term, and this will be correct asymptotics. So there are partial terms and there are exponential terms. In the limit of y goes to infinity, inverse power law grows faster than any exponential term. You know it from mathematics. Exponential term is originating from cotangent, and 1 over y is left here. Okay?
Okay, thank you.
Good. So, susceptibility. I will go with kind of the definition is I'm defining susceptibility per unit volume. So this is N over V, and then I take a limit. H goes to 0, mv divided by H. This is the definition. So, the image which you just had, the problem which we are discussing now, we have some volumes, and there are some spins. The spins are very much being almost classical. Moreover, at this approximation, spins don't talk to each other, so these atoms are distanced so far away from each other that there is no interaction between them. They only talk to the magnetic field. This is the problem which I'm solving now. In next 5 minutes, I will switch to solving a bit more complicated problem, and then more complicated problem, and so on and so forth. For the moment, we have 3 spins which say feel the magnetic field. Okay, now we are ready to compute this quantity. I will denote N node as number of spins per unit volume. So this is N node. And then I will take this limit, saying that I have M, I have Lagrangian function mH over temperature divided by H in the limit H goes to 0. Therefore, I need the behavior of my function for very small value of argument. So this is M node limit M times mH over 3 times temperature minus 1 over 45 mH over temperature cube divided by H. Limit H goes to 0. You see that the first term is linear with H is cancelled out. In the second term, it will be proportional to H squared, therefore it is safely equal to 0. And I am able to write down that this is M node times M squared times 3 divided by 3 temperature. Or, if I denote C as M squared and node of the temperature, I got C of the temperature. So therefore, I obtained first important result, saying that the susceptibility of the system consisting of magnetic moments interacting with magnetic field, local moments, is inversely proportional to the temperature. This law is known as the Curie law. Good. I remind you that...
Sorry, Professor?
Yeah.
I think it's C over 3, not...
Sorry.
yeah. Okay.
Sorry. Yeah. That's the location. Thank you. Good. I remind you other cases which we discussed in the course of many-body theory. When we discussed the paramagnetic situation of a mobile gas of itinerant electrons, what we obtained that the susceptibility is constant, it's proportional to density of states at the Fermi level, plus some corrections on the order of T over Fermi energy square. And the constant is positive. So the response to magnetic field is directly proportional to the magnetic field with a sign plus. When we discussed dimagnetism associated with orbital motion of the electron gas, we obtained that diamagnetic susceptibility is also constant, proportional to the density of states at the Fermi level. However, it comes with a sign minus, which means that the magnetization is induced anti-parallel to the magnetic field applied to it. But in both cases, we had a constant. When we discussed the superconductors, we found out that the superconductors are ideal diamagnets, so superconductors repel magnetic field completely from itself. There is no magnetic field in the volume, so the susceptibility then is also constant. Now we have different behavior. The first case where the susceptibility is inversely proportional to the temperature. Good. Now, let's make the next step in order to take into account interaction between spins. How can we do it? We can first do it phenomenologically, saying that we take one particular spin, this one. So we are dealing with the volume. And we can say that the magnetic field which acts on this particular spin consists of two parts. First of all, it consists of external magnetic field, and then it contains a part which is proportional to magnetization created by all other spins surrounding this one. Therefore, I will write it as plus gamma times mz. Of course, what I'm saying is that I'm dealing with a macroscopic system. It contains very large number of atoms, 10 to the power 23. Therefore, I can forget about difference from the point of view of magnetization, whether this spin is included or not, namely 10 to the power 23 spins minus 1 produce the very same magnetization with accuracy 10 to the power minus 23 as the 10 to the power 23 plus yet another one spin. So I replace the action of all other spins by the average magnetization, average magnetic field created by the field, and I put phenomenological constant gamma, which describes the strength of how this spin is taught to all other conics. Next Monday, we will see how to justify this from the point of view of microscopic theory. Namely, we take some model, for example, Heisenberg-Hamiltonian, and we will see what is the gamma from the point of view of microscopic theory. However, what I said here is very strong and very usable message. It actually opens the possibility to discuss action of all other spins in a way of so-called mean field. I replace, as I say, action of all other spins by its mean value. This is the first case in the theory of 20th century where this average field was introduced, and in the literature it has a name either molecular field or mean field or Weiss field. You can take any name. Weiss field is more specific for the theory of magnetism because Weiss was the first person who introduced it. But mean field and molecular field is widely used in all other contexts of the many-body theory. For example, when we derive BCS equation for superconductivity, we also use sort of the mean field theory because we replace our Hamiltonian by the expectation value, namely energy, so we took some mean values of our in our model. Okay, then let's now look at this equation. Now I replace H by H effective. I can write down that Mz is equal to M Langevin function over M over temperature, and here I have H external plus gamma Mz. Suppose I don't have external field at all in the model, no external field. Therefore, I'm getting equation equation mz is equal to m Langevin function over m gamma mz divided by temperature. So you see, I got some transcendental equation where mz is contained in the left-hand side and in the right-hand side. Let's see how we can solve this equation using the plot which is still on the blackboard. Let me denote this argument of the Langevin function as x is m gamma mz over temperature. Therefore, I will multiply my numerator, my left-hand side and right-hand side over m gamma divided by temperature. I get m gamma mz over temperature is equal to m squared gamma divided by temperature, and here I have Langevin function over x. And this is also x. So the equation which I have is temperature divided by m squared gamma x is equal to Lx. Suppose my temperature is sufficiently high. So the factor in front of the x in the left-hand side of my equation is very big. So it's going like that. So this is a high temperature. You see that the curves cross only in one point, namely x is equal to 0. This is the only solution of the problem. However, if I start to reduce temperature, the slope of the curve goes down, 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 then it hits the tangential, and then it goes down again. So for some temperatures, I have 3 rules. And there is some temperature variation where I hit the tangential. Let's say that this corresponds to critical temperature, this is temperature lower than critical one, and this is temperature higher than critical one. Of course, you can plug in your computer, plot magnetization, and see that at temperatures above critical one, you have only trivial solution. Magnetization is equal to 0. However, below critical temperature, you have 2 non-trivial solutions. One is here and one is there. And this 2 non-trivial solution actually corresponds to the phase transition. This is F with the order parameter phi. So if I'm dealing with a positive, this is this one. Phi node. If I'm dealing with negative, this is this one. So basically, I obtained from this very simple toy microscopic model the behavior characteristic for the second order phase transition. However, we are not with a phase transition theory phenomenology. We are having microscopic equation valid for all temperatures. Therefore, we can identify, for example, critical temperature using this equation. Let's do that. Let's do that. Critical temperature. For the critical temperature, as I said, we should request that the tangential is equal to slope of the slope of the curve is equal to tangential. Therefore, I write this equation as Tc divided by m squared gamma times x is equal to x over 3. I took the first term as an expansion of the Lagrange function. Therefore, Tc is equal to m squared gamma over 3. Okay? If I want to study behavior in the vicinity of Tc, I can expand my equation. So T minus Tc over Tc much smaller than 1. This is the type. So then I have T over m squared gamma is equal to times x is equal to, here I have x over 3 minus x cubed over 45. Where x is, you remember that x is equal to m gamma mz over temperature. So if I multiply by 3 this equation, what I get, that T over Tc, I multiply by 3 and divide by x, is equal to 1 minus x squared over 15. Therefore,
Sorry?
yes,
I don't understand what you're illustrating the tau part of it.
you don't understand what?
The tau part, the T minus Tc over Tc, that's the condition.
This is the condition. I'm going to see how this function behaves in this area. Very close to Tc. Because this is a critical index which defines the behavior of the order parameter, and I would like to show you that this behavior is consistent with the theory, with Landau theory of second order phase transition. This is the definition of Tc. Now I assume that temperature is not equal to Tc. But it is smaller than Tc, but not much smaller, defined by this condition. What I get, that x is equal to square root over 15, and here I have 1 minus t over Tc. So therefore, the behavior of magnetization, x is proportional to magnetization, is precisely square root over modulus tau. This critical index, you remember, I call it beta, is equal to 1/2. This is consistent of Landau theory of second order phase transition. What we see here is actually, indeed, second order phase transition associated with the creation of spontaneous magnetization. You see that you change the temperature and spontaneously you have non-trivial solution, which actually is lower by the energy, and therefore what happens, you apply the magnetic field in your paramagnet. Paramagnet means that magnetization is equal to 0 from the side of high temperature. You reduce the temperature, and then suddenly at some temperature you have spontaneous creation of macroscopic magnetization in the system, so the system becomes a ferromagnet. So to the left-hand side from the critical temperature, you have a system with non-zero magnetization. To the right-hand side, you have a system with a zero magnetization. This magnetization is spontaneously created, so it's associated with spontaneous symmetry break. What I suggest to you as a homework, so non-magnetary homework, is to take this Hamiltonian, to write down the free energy with this Hamiltonian. Actually, I did almost everything for you, because I calculated partition function. So you can write down free energy, you can expand your free energy in terms of the order parameter, and in the vicinity of critical temperature, you should be able to construct Landau function for the free energy and justify that the terminology of Landau used to explain the theory of phase, second order phase transition can be derived from the microscopic model presented on the blackboard. So do it. Write the free energy, namely Gibbs free energy, expand it in terms of the parameter. You see, you have almost all functions written there. And then you obtain what you're supposed to obtain. Okay, so Having said that, we justify that this is a second order phase transition. Let's do yet another exercise before I come to discussion of the quantum model, namely what is the susceptibility. In order to compute susceptibility, by the definition, chi susceptibility is equal to n node, no number of spins per unit volume. You take the limit h external goes to 0 because you need to apply t, see how the system reacts, and then compute. So this is Lz divided by h external. This is the definition. So I continue this line. So this is L node, limit h external goes to 0, and I will plug in my magnetization. So this is M Lagrangian function over M of temperature, h external plus gamma magnetization, divided by h external. Since h external goes to 0, I can expand my Lagrangian function assuming the argument is small. Whole argument is small because I'm also assuming that magnetization here is small compared. So I'm in the paramagnetic area, if you want. I'm here, so in this region I'm assuming that induced magnetization is also proportional to magnetic field. I will comment on what happens for temperature smaller than the critical one. So therefore, I'm allowed to expand my Lagrangian function. So this is M node, limit h x goes to 0. The first term is M square h external over 3 temperature divided by h external. And the second term is M square gamma Lz divided by 3 h external temperature. Here, h external cancels out. M square M node over 3. This is C. So this is C over temperature. This is the first term. Or I denote it as a chi node. But the second term, you see, I have the same magnetization over temperature plus M square gamma over 3 temperature times M node limit magnetization Lz divided by hx goes to 0. But this is the definition I began with. So this is the same susceptibility. Therefore, I can write it down here, collecting everything what I have, and also notations that chi is equal to chi node, M square gamma Tc is equal to M square gamma over 3. So this is Tc over T plus Tc over temperature times chi. So I got this equation which has a solution that chi is equal to chi node divided by 1 minus Tc over temperature. Or this is C over temperature divided by 1 minus Tc over temperature. Or chi is equal to C over Tc, 1 over T minus Tc over Tc. Okay? So this is what we obtained. Namely, we obtained that the susceptibility of our system diverges when you approach approach to the critical temperature. This law in the literature is known as the Curie-Weiss susceptibility. So contrast to system of non-interacting spin, where the susceptibility is divergent when the temperature goes to zero, here the susceptibility diverges when you approach the critical temperature. Typically, experimentalists like to draw inverse susceptibility as a function of temperature. You see that it goes linearly, and this is Tc. By the way, when we discussed on the theory of phase transition, we also obtained that susceptibility in the vicinity of phase transition point diverges as one of the tau. You recognize that here the tau. So therefore, it's yet another confirmation that we have a second order phase transition. So what happens for the temperatures below Tc? Below Tc, the susceptibility is equal to infinity, because you have spontaneous formation of moments, which is non-zero even in the presence of zero magnetic field. Therefore, in your definition, mz is non-zero, h external goes to zero, therefore your susceptibility is equal to infinity. So the inverse susceptibility is equal to zero. So this is what we obtain from the very simple microscopic model, assuming that we have a molecular field theory. Okay? Good. I have 40 minutes, and let's be quantum. Let's go to the quantum part of the theory. Clear? Okay. What I'm going to say now is equally applicable for the very quantum spin, namely spin 1/2. And most of the thing which I'm going to show you now will be very similar to the semi-classical theory of the magnet. So now I'm in the quantum part of the theory. Quantum means that I'm dealing with operators, and you need to discuss the total momentum of your atom. The total momentum, which I denote J, this is operator. It consists of the orbital momentum and spin. You sum them up using quantum mechanical operators. So the magnetization of the system, total magnetization, because it can be associated with orbital and spin degrees of freedom, is equal to the lambda factor, which I denote as Gj, Bohr magneton, times the total momentum J. This is a total magnetization quantum mechanical operator. What is what? First of all, the Bohr magneton. Bohr magneton, we introduced it in the lecture number 3. This is modulus E h bar over 2 mc. This is Bohr magneton. Gj is lambda factor. Or G factor. Without derivation, I assume that in advanced quantum mechanical course you consider spin-orbit interaction, then this Gj from your quantum mechanics notion is equal to 1 plus J plus 1 minus L plus 1 plus S plus 1 divided by J2 J plus 1. One can derive this lambda factor. If you forgot how to do it, I assume that you take a textbook and you repeat it. This is combination of spin and orbital degrees of freedom. two important cases. Important case number one, where your total momentum, so this is the total momentum, consists of your spin. There is no orbital degrees of freedom. So L is equal to 0. Then J is equal to S. Then GS is equal to 1 plus SS plus 1 plus SS plus 1 divided by 2SS plus 1. So this is 1 plus 1. It is equal to 2. The geomagnetic ratio or G factor or lambda factor is equal to 2 when you have your total momentum equal to your spin. This is what we used for spin 1/2. I told you that G factor is equal to 2. Actually, G factor is equal to 2 for any system where the orbital momentum is equal to 0. Then,
excuse me, Professor.
yes.
Yeah, for the purposes of discussion, I think we started from the semi-classical theory and we derived various important properties for the magnetism. I want to ask, we have started discussing also from quantum mechanics perspective. What are the failures that we've seen in the semi-classical theory? Can this only be seen if we do this from quantum mechanics, that we see differences, or can we state categorically from the semi-classical theory?
Good question. I told you that semi-classics has a limited domain of applicability. Namely, rigorously, it's only applicable when your spin is macroscopically large. So this is much bigger than 1. However, in reality, we often have a situation where spin is not large. For example, spin is equal to 1/2. So clearly, semi-classical theory is not applicable for that case. And we need to start with a different grounds to build in the theory. We cannot rely on semi-classics anymore. Therefore, I want now to make a step back, start with purely quantum mechanical description, having no assumptions about the value of your total momentum, derive equations which will be different from the equations which I derive in simplified semi-classical theory. But then I will see, if I take this assumption, this semi-classical limit, how can I reproduce the known equations? Yes, I will reproduce all semi-classical equations from the quantum mechanical theory, but not other way around. Maybe in addition, I will also get a correct description for the behavior of magnetization for the very quantum limit where spin is not large, which is of the order of 1. Okay? So this is the logic. I don't want to do opposite. In principle, I can start immediately with quantum mechanical theory, derive everything, and say this will be classical limit. But before doing that, because in several cases, semi-classics is more simple way to think and more simple way to derive, I wanted to show you how to get results almost for free, and then I need to switch hard in order to get some other results. Okay?
Thank you, Professor.
Good. So, second important case where spin is equal to 0 and your magnetism, your total momentum, is fully related to the orbital degrees of freedom. If F is equal to 0, J is equal to L, this is L plus 1 minus L plus 1 is 0, and GL is equal to 1. When you have both non-zero orbital degrees of freedom and non-zero spin, you have your lambda factor. Good. Now, I need to discuss the average magnetization. The average magnetization, first of all, I will write, this is semi-classical. The quantum Hamiltonian will be the very same. This is minus G mu Bohr J times H. I just plug in the value of M. Written there. Therefore, in order to compute the average magnetization, I will compute it using the same Gibbs distribution. But now, contrast to what I had before, I assume that my operator G, Z, has a diagonal form, and therefore it can take 2f plus 1 weights. So the eigenvalues of GZ are varying from minus G plus 1, G minus 1, G, and in total there are 2 J plus 1 weights. JZ is diagonal in this representation. JZ squared is always diagonal and equal to J plus 1. So therefore, by the definition, I replace integration of a sphere of a solid angle by summation of eigenvalues. So this is Gj mu Bohr. In the numerator, I have a sum over m equal to minus j to j, m e to the power minus Hamiltonian over temperature, and in the denominator I have m equal to minus j to j e to the power minus h over temperature. So these are values of m projection. So this is the definition. Okay? And as before, I define the partition function, which is denominator, which is sum over m equal to minus j to j. Here I have e to the power plus gj mu Bohr h m over temperature.
Hello?
Okay?
Hello?
Problem?
Professor?
Yes.
Sorry, I have a question. Sorry to take you back, but in the graph of the susceptibility in the semi-classical approach, the one you still have there, why is it that below temperature, critical temperature, you have it as a constant 0?
This is chi minus 1. Because, as I said, below TC, you have your magnetization. This is your magnetization. This is TC. If you are below TC, for example here, you have a finite value of magnetization. Therefore, and this magnetization occurs due to spontaneous symmetry breaking. Therefore, it's not sensitive to magnetic field. And by definition, susceptibility chi is Mz divided by H external in the limit H external goes to 0. You have a finite and you go H external equal to 0, you have infinity. That's it. You have a finite macroscopic magnetization which exists in a zero field. Therefore, by the definition, susceptibility is infinity. And no susceptibility is 0.
Okay, thank you.
And this is the partition function. And let me first calculate it. I remind you that in classical situation when we had a sphere, we said that our magnetization vector is continuously distributed on a sphere. Of course, if your j is very large, you can then replace the delta j will be equal to 1. It's very small compared to large value of j. You can then replace your summation of a discrete values, eigenvalues, by the integration. This is how you get the integrals. Before, I'm not going to compare it on each and every step. I will compare it in the final results. So z. Let's denote again x is equal to gj mu Bohr h divided by temperature. So z is equal to sum over m equal to minus j, m equal to j e to the power m times x. minus jx plus e to the power minus j plus 1 x plus e to the power jx. You have 2j plus 1 terms. If I take out e to the power minus jx, what I have here, I have 1 plus e to the power x plus e to the power 2x plus e to the power 2jx. You remember that your orbital momentum has always integer eigenvalues, your spin has an integer and half integer values, that whatever you have, when you sum up quantum mechanically j, l and s, you will get either integer or half integer. And in both cases, 2j, the eigenvalue, will be integer. So, I have geometric progression with a finite number of terms, so I will multiply by 1 minus e to the power x, and what I will get here is this, minus jx, and I have 1 minus e to the power 2j plus 1x. Good. This is summation of the geometric progression with a finite number of the terms. So therefore, I continue here. It is equal to e to the power minus jx plus e to the power j plus 1x, so minus, divided by 1 minus e to the power x. So I will invert signs in numerator and denominator. E to the power x minus 1, e to the power j plus 1 x minus e to the power minus jx. And I will multiply my numerator and denominator to the power e x half, e to the power minus x half. Good. What I get here, I will get e to the power x half minus e to the power minus x half, which is already good. It gives me something like sinus hyperbolicus, twice sinus hyperbolicus, and I have e to the power j plus 1 half x minus e to the power minus j plus 1 half x. Great. Therefore, I can write down that my partition function z in quantum case is equal to sinus hyperbolicus j plus 1 half x divided by sinus hyperbolicus x over 2. You should compare it with a classical case. No assumption. Now, what about numerator? What about numerator? Let me restore the equation which I wrote down and see. So this is sum over m equal to minus j to j, m e to the power mx. So this is x. Therefore, numerator is equal to gj mu Bohr, and then it is equal to d over dx of my partition function z, if x is equal to gj mu Bohr h over temperature. Right? Because if I differentiate my partition function, this is sum over n equal to minus j to j e to the power mx, I will get that. Therefore, let me now compute this derivative. So this is then equal to gj mu bar. I'm differentiating the fraction. So therefore, I have sinus h squared x over 2 in the denominator. So I have j plus 1/2 cosinus hyperbolicus j plus 1/2 x sinus hyperbolicus x half minus sinus hyperbolicus j plus 1/2 x times cos hyperbolicus x half, and there is 1/2 here. This is the derivative. If I combine everything, I can write down the mz is equal to gj mu bar. So I need to divide by z. If I divide first term, I divide the first term, so I have a sinus square, which cancels out with denominator, and I have a cotangent j plus 1/2, cotangent j plus 1/2 x. Good. And if I consider the second term, I have sinh, which cancels out with this one. I have 1 power of sinh cancels out, so I have minus 1/2 cotangent x half. Great. Now I would like to introduce a new variable. I would like to write it as a gj mu bar j x over t times times 1 over g. Like this. Good. And I denote this variable as y. So therefore, what I would like to write down that y is just equal to j times x. And therefore, I will take out j from this summation. Mz, just follow me, is equal to gj mu bar j. I have 1 plus 1 over 2j, cotangent hyperbolicus. So x is equal to 1 over j, so this is 1 plus 1 over 2j times y, minus 1 over 2j, and this is a cotangent hyperbolicus y over 2j. Now this function, which I have in the right hand side, is called brilliant function. So it has index j and argument y. Good. I introduce a new function. I will rewrite it again. The brilliant function bj y is equal to 1 plus 1 over 2j cotangent hyperbolicus 1 plus 1 over 2j y minus 1 over 2j cotangent y over 2j. Brilliant function. And my equation reads that mz is equal to G, J, mu, bar. J and Brillouin function J with the argument G, J, mu, bar, J, H of temperature times Y. Good. In the classical limit, I have Langevin function. In the quantum limit, I'm getting Brillouin function. Let's see the properties of Brillouin function. Are there any questions about derivation of how I get it? It's not an approximation of geometric progression. However, I did not make any approximations in order to do it. So, properties of a Brillouin function. Property number 1. We see that the Brillouin function is odd function of its argument for any y minus b, j, y. Which means we can consider it for positive values of argument and then take a reflection with respect to the origin. Second, let's see how this function looks like for fixed j but for small argument. Y goes to 0. In order to do it, we Taylor expand. So this is, let me do this expansion here. I deliberately spent so much time to discuss the properties because after I finish it, everything else will be very clear. So bj, y goes to 0 is equal to 1 plus 1 over 2j. I need to expand cotangent. Cotangent is 1 plus 1, the inverse argument, sorry. It's 1 divided by y, 1 plus 1 over 2j, minus plus y, 1 plus 1 over 2j over 3. This is the first term. Minus 1 over 2j, 2j over y, plus y over 2j, 1/3. I take into account only first term in the expansion. So now, it is equal to, first term here is 1 over y. Second term here is y over 3, 1 plus 1 over 2j, square, minus first term in the expansion here. It's 1 over y. Sorry, I put a wrong bracket. The bracket is here. Minus 1/4 y, 1 over 2j square. Good. So the terms 1 over y cancel. And we have y over 3 times 1 plus 1 over j. So this is y over 3, j plus 1 over j. So this is y over 3, j plus 1 over j. Again, if we take limit j goes to infinity, we get y over 3. Property number 3. Let's take semi-classical limit b, j goes to infinity, y. So we need to make yet another expansion. So b, j goes to infinity over y. So, this is cotangent y. From the first term, I take j equal to infinity immediately. And in the second term, I need to expand. Need to take the first term in the Taylor expansion. So this is minus 1 over 2j, 2j over 1. all the next terms will be proportional higher power of 1 over j, so it goes to 0. So this is cotangent y minus 1 over y, so this is a larger than function over y. So this is what I need to show, that if we assume some classical limit, we get a transformation of our Brillouin function, which describes both truly quantum mechanical limit and semi-classical limit, but in this particular limit, when we have a large semi-classical total momentum, we have a larger function which replaces one Brillouin function. And this was a good exercise. And the exercise number 4 is to show how this Brillouin function j y behaves at infinity. Since I have only 10 minutes, I leave you this exercise, but I will write the answer. You need to do the same as I did for the Brillouin function. So this is y minus 1 over j e to the power minus 1 over j. So which means that this Brillouin function is also limited from above and below. So it's defined in stripe, and it looks pretty the same as Brillouin function j y and the function of y. Good. So now we repeat basically the very same things which we did for the classical system. Namely, if we define the susceptibility chi node, which is equal to N node limit over mz divided by h external, if h external goes to 0. This is equal to N node number of spins per unit volume, g j mu var, limit j over h goes to 0. And if we Taylor expand using these properties, what we will get, that this is equal to N node g j mu var square times j plus 1 over 3 temperature. Again, instead of m square for the classical limit, where m was the length of your classical vector, we get correct value over j square, which is j plus 1. Again, we see correspondence between classical and quantum, semi-classical and quantum compositions. Therefore, we can write down that chi node is again equal to C node over temperature, where C node is N node G mu bar square J plus 1 over 3, and this is Curie law. Pretty the same logics. The logic number 2. We consider the system of spins and apply the molecular or mean field scheme for calculations. Therefore, we will get the pretty same T smaller than Tc T larger than Tc, T smaller than Tc, and when tangential, this is Tc. We see again that there is spontaneous magnetization which actually appears at the temperatures below the critical temperature. With the same logic, you replace the argument of the Brillouin function here. You replace magnetic field by external magnetic field plus molecular field, again gamma times magnetization. You do these calculations and you compute that Tc is equal to Gj mu bar square j plus 1 over 3 times gamma. Please repeat these calculations. I'm not going to do it again on the blackboard. This is a critical temperature for the quantum model. Again, no assumptions about value of the total momentum. Equally applicable for the momentum of the order of quantum and for the large semi-classical model. And last calculation is that you define your chi as f naught limit of mz over h external goes to 0, assuming that you have some non-zero reaction, and you will get the same equation as before, that chi is equal to chi naught plus Tc over T chi, or chi is equal to chi naught over 1 minus Tc over T, or this is C naught over Tc, 1 over T minus Tc over Tc. So you see that all quantities C naught and Tc are defined here. So the susceptibility behaves pretty the same way for the quantum model as compared to classical. The only thing which you need to follow is that to replace the length of the classical vector square by the eigenvalue of the operator j squared, which is j plus 1, and take into account the constants which are lambda factor of the magnitude. Again, the susceptibility diverges at some finite temperature, which is a critical temperature, and this describes what happens with the ferromagnets. Where the ferromagnetism is associated with local degrees of freedom. This is, for example, like, well, with some reservation, like iron and nickel behaves. So when you have iron, the critical temperature, or Curie temperature, so this is a Curie temperature, is also 600 kelvins. So when you take your piece of magnet and heat it higher than 600 kelvins, it is non-magnetic, it's paramagnetic. However, below this temperature, your piece of paper can be used as a tissue paper. Your piece of iron, magnetic iron, can be used in the magnet, so these magnetic properties of iron and nickel are related to spontaneous created magnetization, so the total magnetization is not equal to 0, and the susceptibility behaves the very same way. Next week we will see how the same properties appear from the microscopic model, from the perspective of the microscopic model, and yeah, that's basically all what I wanted to tell you about the theory, the simple molecular field theory of local magnetism, which we consider from both semi-classical and quantum point of view. Any questions? No questions. You need to digest it. Good. If you have no questions, I will explain what we are going to do Friday. On Friday, we will consider complementary problem, namely what happens with a magnetic moment if it is a subject of time-dependent magnetic field. So we will discuss the precession of magnetic moment, oscillations. We will derive the susceptibility as a function of time-dependent susceptibility, or frequency-dependent susceptibility. We discuss properties of this susceptibility and application. Because the problem which I'm going to discuss Friday is very much related to modern problem of manipulation of qubit with a qubit, because qubit basically it's two-level system. one can think about it as a spin 1/2. So this is what we are going to do on Friday. And next week, last 2 Blackboard lectures will be devoted to behavior of ferromagnets below critical temperature and above critical temperature, and antiferromagnets in terms of the Heisenberg model below critical temperature and above critical temperature. And last lecture, next Friday, will be done with the slides. This will be a summary. It will be devoted to strongly correlated systems. So it will summarize the knowledge of superconductivity with the roots to high temperature superconductivity and magnetism with the roots to magnetic properties of exotic strongly correlated systems, and the competition between different phase transitions like magnetic and superconducting transition, which is the core of the behavior of the high temperature superconductors. These are the plans for this and next week. And yes.
I have a question. What is the difference when you take the limit of h external goes to 0 and when you take h goes to 0?
Well, sometimes I didn't discriminate. I always say that the susceptibility is defined where the h external goes to 0. If your models don't talk to each other, h and external field, there is no difference. If your models talk to each other through this molecular field way, then you have external field and effective field. So, but the susceptibility is always defined as a limit when you take external field and put it equal to 0. We come to this point. Yeah.
Yes.
Please, keep saying.
I think it's in the Blackboard. First you wrote limit h external goes to 0 and then equal to n naught g. Yeah.
Well, sometimes I forget to write index. If you are talking about this, this is also external.
Yes.
This is external. Because there is no difference here for chi naught when the models don't talk to each other, because this expression doesn't contain gamma. Everything which doesn't contain gamma, this is attribute of your molecular field theory. So for everything what doesn't contain gamma, there is no difference between h and h external. So sometimes I forget to write down the subscript.
Okay, thank you.
Professor?
Yes.
You told us that the gamma is a phenomenological constant. So
Yeah.
how does that arise, say, in the experiment?
Well, first of all, you see here that there is a connection between Tc and gamma. Tc is proportional to gamma. Therefore, measurement of critical temperature is sort of way of measuring this parameter. How it is connected to microscopic model, like Heisenberg model or Isaac model, I will show you on Monday next week.
Okay, thank you.
Okay, more questions? Don't forget about homework. Now you are almost ready to solve everything. Well, maybe last 2 problems still, but I hope that by the beginning of next week, by Monday next week, you will be able to solve everything. And this concerns only the last problem. Good, and I don't plan tutorials for the magnetic part. I think you start soon some other courses. And anyway, what I'm going to say for magnets will be closely related either to the basic things about second order phase transition or basic knowledges of thermodynamics, which you already discussed with Andrei in the course of statistical mechanics. Okay, good. If no more questions, we are done